Hi everyone, this is Joaquin van Schoren, and welcome to the third lecture of our machine learning course, which is all about kernelization. Now, kernelization is a really cool technique to make linear models nonlinear and learn many more complex models. First of all, remember what a linear model is. Right? So it's a model where our prediction is a linear combination of our input features, and we want to learn a set of weights, W, or coefficients, that will ensure that we get the correct output giving the right input. Right? And so exactly this is a sum of, it's a linear combination of a number of weights times always the value of the ith feature in our data set. Right? So remember, our data set has a number of columns, p in total. We learn a weight for every column, and then the sum of the weight times the value of each row will give us a prediction for that row. Okay. Now, we saw that there are many cool techniques that we can use to learn these models, but when they cannot fit the data well, there's nothing we can do with the models themselves. But what we can do is we can add a number of extra features to our table which allow us more weights to learn, and hence we can also learn more complex models. Now, important to make sure that our models don't remain linear, we want to make sure that those extra features are a nonlinear transformation of our original features x. Right? So we want to learn a transformation, a nonlinear transformation. We call that phi here. So that given our original features x, it produces a d-dimensional, d-columns, d-dimensional space in which our points then will live. Right? We call this in general a feature map or a basis expansion. Right? We start from an existing basis and we expand that, we map that to a larger, more high-dimensional space. Right? So that means that our model, our linear model, now becomes this. It's a linear model, but it operates on a much larger space of features. Right? One very well-known example of this is the polynomial feature map. So given our features x, 1 to p, 1 is to record our bias, our feature map will produce our original data, original features, all the squares, all the third degrees, and so on, up to the dth degree for all our features, plus all the combinations of all our features, right? So x1 times x2, x1 times x3, and so on up till xp minus 1 times p sub pi. Right? So this is a pretty dramatic expansion of the number of features, especially if p is large and d is large. To give you one very small example, so say that p is 1 and d is 3, which means we only have one feature, and we want to raise that to the third degree. Then we get original features plus a new weight times the square of our feature x sub I, 1, and another weight times x to the third degree. Right? There's no interactions here because I only have one feature, but it's a simple example. Right? So you see that this gives us extra weights that we have to learn. Does this actually help us? Well, this is some data. And if we fit a linear regression to these points, we only have one input feature x, and that's the output. Because we only have one input feature, we can only learn one weight. Or there's a bias as well, which is not shown here, but there's a bias as well, of course. And now, by adding these features, we can learn more complex models. Right? So we can actually learn a very, like you see here, like you can learn a very complex nonlinear function over inputs simply by adding more features, right? And so the only thing I do is I take my original feature and I add here the second degree, third degree, the fourth degree, fifth degree, and so on, all the way to the 10th degree. Right, so this is just this value squared. This is this value squared up to and so on, right? So, of course, because we take the 10th degree, these numbers will be much, much larger than initially. That's the idea. If you want to try it yourself, sklearn has a polynomial features transformer you can use for that. Okay, so now we see we have to learn not one weight, but 10 weights. Right? So and after we learn those weights, so again, I use normal ridge regression here. I just have more weights to learn. Right? And if I then map the result y in function of our input x, we get this very nonlinear function. Right? So it's a super powerful technique, and we can basically learn models of any complexity by using this trick. However, this is very expensive, right? First of all, you may need many dimensions, right? Here I added 10 new dimensions for a one-dimensional data set. If you have a 100-dimensional data set, it's going to explode. You'll have a lot of features to deal with and a lot of weights to learn. Right? So first of all, this adds memory because you have to, first of all, learn all those weights. You have to construct all those features. So you have to do all these computations here. So that will require a lot of memory and a lot of computation. It also means that you will have a lot more weights to learn, and if your model has a lot of weights, it's also very easy to start on a fitting, to start overfitting your data, of course, right? So in this case, already you see that the data matches, of course, the points quite nicely here, but if you take it too far, you'll get very complex, very highly oscillating lines through this space, and that will not work well. Okay, so just to do some calculations. So remember that ridge has a closed form solution, which we can compute with linear algebra, right? Which looks like this. This we saw in the previous lecture. Now we are going to use a transformation. So this original non-transformed ridge has to compute this X transpose X matrix, which is a D by D matrix. So X is D features and rows. So XTX gives you a matrix which is D by D. And so it's D columns and D rows. And then we have to take the inverse of that. And this will mean that doing this calculation is quadratic in the number of features D, right? Which is bad enough by itself, right? But now, if we are going to use a feature map, it means we're going to feature map our inputs X. And if this transformation gives you an order of magnitude more features, it's going to explode this number even more, right? It will not be a quadratic, it will be very high polynomial. So it will be a huge amount of compute to actually compute all, well, first of all, to construct this space and then to learn all those weights. Right? So it's a nice technique, but in practice, it is often too expensive to do, unless your data set is quite small. Now, and so the same problem we find with linear classification models. This is here we have a linear SVM. We have some data points, we have red points and blue points, and we see in this case we cannot linearly separate those data. Right? What we can do, however, we can take one of these features, feature 2 for instance, and we can do the exact same thing as before. We're just going to add the square of our features. Right? So in that case here, this feature here is just the square of this feature, right? Which means that points close to 0 will remain unchanged. Points far away from 0 will be changed a lot, right? So, of course, if you go 10 to the second degree is 100, so all these points that are here, they're going to move down. Well, this is inverse scale, so they go up, and these ones as well, right? So, just by adding this one feature here, we transform our space. Now, it's just a 3D because that's all I can plot. But in general, you can see that if you do this, you can move these points away from each other, right, in this high dimensional space. And by doing that, you can learn a linear hyperplane through these points, right? So that's all I did is just adding an extra feature, and now this data becomes linearly separable. Of course, you don't. I was sort of lucky, and I engineered this a bit, so I know I only need the square. In general, you don't know which kind of transformations you typically need, right? So that's another question. But if you would have a good transformation of your data, it's more likely that your data will become more easily separable. Right? If you would then plot that again in function of feature x and feature 1 and feature 2, now our output, so this was our original linear model. We add one new feature with the square of x2. We learn this new weight w3. And if you then plot this y, we see that we now learn this decision boundary here, right? Which is now a polynomial itself. Okay? So the same trick, but just by adding new features, we can learn much more complex models. But again, it's expensive. So, however, we don't necessarily need to construct this space, right? So we don't necessarily need to construct this whole table. The only thing I need when I use support vector machines, for instance, I only need to compute distances between a point and my support vectors. Right? So what if I can do just that? What if I can just compute distances in this high dimensional space without actually constructing them? Right? That's the whole idea. And it turns out you can actually do this. So let's say, for example, we take the quadratic feature map, which looks like this. So it's our inputs, x1 to xp, we add all the squares, and we add all the combinations of all the features times square root of 2. For this feature map, there exists a kernel function. A kernel function is defined as this. So a kernel function is basically a dot product in a higher dimensional space. That sounds scary if you've never seen this before, but it's actually quite simple. So instead of computing the dot product between two vectors, xi and xj, which is the projection basically of this point on this hyperplane here, we do the same thing after transformation. Right? So we transform this point to high dimensional space, this point to high dimensional space, and then we compute the dot product again, but in this high dimensional space. Now, if you construct this hyper high dimensional space using this feature map, it turns out that this dot product of any 2 points equals this. So it's just the dot product of my original features plus the dot product of our original features in our original space squared. So nowhere here do I need to construct this high dimensional space. If I want to know what is the dot product of, actually more precisely, what is the kernel between our 2 points xi and xj, the only thing I need is to compute this, right? Which is super cheap, right? It's just 2 dot products. But it's 1 dot product and then squared. But so we don't have to compute these guys at all, and we can just compute the kernel directly. Okay. So that's the whole idea, right? So we have a low dimensional space with 2 points xi, x1, x2. We plot those of them using the feature map, which ends up in this high dimensional space. In this high dimensional space, we also have an origin. We compute basically the dot product of these 2 transformed points, and then we learn this, which is exactly the dot product in this high dimensional space. Okay. So basically, what a kernel is it's nothing more than a generalized dot product. It's a dot product computed in a high dimensional space. This high-dimensional space, H, is more generally called the reproducing kernel Hilbert space. You don't have. So the meaning of that is that it's a space that's created by a reproducing kernel. The kernel basically produces a space, or the feature map that's linked to that kernel construct that space, and this was invented by David Hilbert. Right? So whenever you hear people talk about Hilbert spaces, that's the only thing. That's the high-dimensional space, which is typically virtual, right? You can reason about it, but you don't actually have to construct it. Okay, now since a dot product is a measure of the similarity between 2 points, right? Remember the dot product. I have 2 points here, x1, x2. If x1 and x2 are in the same direction of the space, which means they have a small angle, right? Then the dot product will be high, right? If they are in different spaces, the dot product will be very small, or if they are opposites, then the dot product will actually be negative, right? So yeah, so if a dot product is a measure of similarity in our original space, then the kernel, which is nothing more than a dot product in a high-dimensional space, can be seen as a similarity measure for this high-dimensional space. Right? So that's actually the easiest way to think about it. So when you see a kernel, is basically a way to measure how similar 2 points x1, x2 are in a high-dimensional space. Okay. Why is this useful? Why? Well, because if we have a machine learning algorithm with a loss function, which is based on a dot product, we can simply replace this dot product by a kernel. This means that instead of computing dot products in our original space, we can compute dot products as if our data was living in a high-dimensional space, as if we would have constructed this high-dimensional space. Right? So we don't have, again, we don't have to build a high-dimensional space, but we have basically a shortcut to compute the dot product between points. And more generally, when we have a loss function in which the inputs only occur as dot products, we call that loss function kernelized. Okay. Now, just as a short summary, so a kernel is basically just a similarity measure between 2 points in a high-dimensional space. And what a high-dimensional space is, we can choose based on the kernel that we choose. Okay, let's use this in practice first of all. So remember our support vector machines. Now remember when we used, when we basically derived the loss function of our support vector machine with the Lagrange multipliers, we found that it had 2 solutions. It has a primal solution in terms of the weights of the features, and it has a dual solution in which the loss is defined only as a function of the dual coefficients. And the dual coefficients are just a weight coefficient learned for each data point I. Okay, and so intuitively, of course, say, just to remind you how this works, right? So say that we have 2 points xi and xj. If those 2 points are close together, so say that this is xi and this is xj, and these 2 points are close together, right? If those 2 points are close together, then the dot product will be high. Okay. Now, if those 2 points have the same class, say that they're both positive, then their signs will be both positive, this will be negative, and the loss goes down. Right? So that's good. If you have points close together, which are both of the same class, the loss goes down. If, however, this is not positive but negative, then that's bad, because we don't want points close together to have a different class. Right? It means that there's a decision boundary running 2 points which are close together. In that case, again, because they're close together, this will be high, but these will be opposite. One of these will be negative, one will be positive, which means this component will be positive, and we add to the loss function. Right? So whenever we have 2 points close together with a different sign, our loss goes up. Right? And so we're trying to minimize our loss by adding a coefficient alpha I and alpha j to each of these points. In this case, of course, we want them to be classified correctly. So this means typically they will get a higher coefficient for that point. That point is important to get right. So remember, the whole reason why we were discussing kernels was this. If we have a loss function in which the inputs only occur as a dot product, then we can simply replace this dot product by any kernel of our choosing. Right? So now the kernel is part of the loss function. And simply by doing that, we can make a linear model nonlinear. Right? So again, here we have a bunch of points, and this is the linear decision boundary learned by linear SVM. Simply by plugging in this kernel, we can learn now very complex decision boundaries using the exact same algorithm. But nothing changed. We're just only learning support vectors, and we're learning their coefficients. That's all we do. It's still a linear combination, but because we have the kernel, basically what changes is the way that we measure distances between those points, right? So now it's not something like a Euclidean distance. Now this is the distance in a high dimensional space, right? Which means that we can, if you would want to compute distances between points, this will be slightly different. Right? That's the only thing that changes, right? So we replace our dot product by a kernel, by a generalized dot product, which implicitly will compute the dot product of these points in a very high dimensional space. Right? So these points now are somewhere in a high dimensional space. So this point goes there, this point goes there, and now the dot product changes, right? The kernel is not the same as the dot product. And that will mean that the similarities between the points change, which will then also change our predictions. Right? And then we end up with these curved decision boundaries. Right? So that's pretty cool, right? So we have done almost nothing. We've just replaced our dot product by a kernel, which is a very simple operation, and we can learn now very complex decision boundaries. Okay, so this is nice, but which kernel exists? Right? Now, the theory says that kernel, or more specifically a Mercer kernel, is any function that takes 2 inputs, xx, and outputs a real value number out, which is the similarity of those 2 points. Right? Of course, this needs to be symmetric, right? So the similarity between 1 and 2 is the same as the similarity between 2 and 1. And secondly, the kernel matrix must be positive definite. So the kernel matrix is simply the matrix of all the possible combinations of features, inputs. And so all the possible combinations of inputs. This is an n by n matrix. And so at any point, it has the combination of 2 features and computes a kernel for that combination of features. We also call this a Grau matrix. And this matrix needs to be positive semi-definite. What does that mean? Well, intuitively, first of all, if our similarity function is always larger or equal to 0, then it will be positive semi-definite. There's no question. There are also cases where this is not true, but the kernel is still positive semi-definite. One example is the linear kernel, for instance, which has a property. Dot product can be negative, but still the kernel matrix is positive semi-definite. Okay, so that's if you can find a kernel, or if you even can just define some measure of similarity and construct this kernel matrix, then you're done. Then you can use it, right? So you don't even need a kernel function, like a reproducing kernel. If you can just construct a kernel matrix, then you can also use that to build a support vector machine. And we'll see some examples of that later. Okay, now learning about building this this matrix here is this an n by n matrix, so it's complexity n squared. That's a bit of work, but after that we can simply look up all the kernel values of any 2 points. Okay, in the practice again, you can either supply a kernel function if you have a problem for which a kernel function does not exist, like for instance if you work with text or images or data or graphs, then there is no really a kernel function for that, but you can use any other similarity to pre-compute the kernel matrix. And you can still then use kernelization, you can still use kernelized support vector machines. We'll come back to that. So for now, assume that there's a kernel and we can use that. So which kernels exist? First of all, there's linear kernel, which doesn't do anything really. So this just maps our features into the same space, right? So nothing happens, and the kernel of 2 input points is simply the dot product of those 2 points. And again, we can see this as a measure of similarity. This becomes larger if the 2 points are in the same direction in the space. It also becomes larger if the points are far away from the origin. Yeah, that's the linear kernel. So if you have, so this plots the value of the linear kernel for a certain angle. Right? So if we have one vector here, so it's a unit vector, and we have one vector at a slight angle, then we end up here, right? So if you have 2 vectors close together, so if the 2 vectors are the same, then the similarity is 1. Right? If they are at a slight angle, the linear kernel goes down again. If they are at 90 degrees, it will be 0. If it's more than 90 degrees, it will be negative. So that's the linear kernel. The polynomial kernel can actually be constructed out of other kernels. So there's a rule that says that if we have 2 kernels, then any scalar times our kernel is also kernel, any sum of 2 kernels is also a kernel, and any product of 2 kernels is also a kernel. Right? And so any combination of these is a kernel, and the most obvious example of this is a polynomial kernel, which is defined like this. So it's the dot to this is a dot product of the 2 vectors, x1, x2, times a scalar gamma plus a scalar c0, and that d times, multiply d times, so it's to the degree d. This is a kernel that belongs to our polynomial feature map. Right? So if we use a polynomial feature map to basically add more dimensions, then the dot product of any 2 points in the high dimensional space is exactly this. Right? That's a nice property. This is a very useful kernel. It has a few parameters. So one is gamma here. Gamma is basically just a scaling hyperparameter. By default, it's 1 over the number of features. But if you want, you can also play with that a bit. C0 is a hyperparameter that traces off the influence of the higher order terms. So if this is 1, then all the features are equally important. So both the low dimensional and the high dimensional, like both x to the second and x to the deep have the same influence. If you make this smaller, then you put more emphasis on the lower order terms. If you make it larger than 1, you put more emphasis on the higher order terms. Right? And sometimes that's useful to play with. This is a kernel that we get. So this is basically, again, this is the same idea. So we have a vector at 0, and we have another vector at a certain angle. And basically, it behaves similarly to the linear kernel, but it's much steeper. Right? So this is degree 1. If we add higher degrees, you'll see that this kernel becomes steeper and steeper. So the distance does not linearly change, it changes polynomially. Right? This becomes, if degree becomes large, this becomes a very steep, very high value. You can also change the gamma function, which will have another influence, and the coefficient 0 as well. So you can see what the effect is. Typically, these have much less effect, and they have good defaults. So in practice, you can often keep this to default, and you basically play with the degree to control the complexity of your model. So a lower degree gives you a simple model. A degree 1 gives you, again, the linear kernel. If you have a higher degree, it becomes nonlinear, and the more degrees you have, the more complex the model becomes. Right? One of the most useful kernels is RBF kernel, or the Gaussian kernel. This kernel corresponds to a feature map which builds the entire Taylor series expansion of e to the x. This is in principle an infinite series, right? So this means that this feature map in principle builds infinitely high dimensional space, with the caveat that, of course, the higher order terms, because we have one over gamma here, the more higher order term gets, the smaller the influence gets. Right? So the first ones have more influence than the last ones. The Taylor series is a way to approximate any function gradually. Right? The first components have a big effect, the large ones have a small effect. All that is not so important. What is really important is that this is a very flexible space, right? So we can, if you would be able to construct it, we could learn basically any possible function. But we don't have to construct a space because we have a very nice, simple kernel for that, which looks like this. It's just the exponent of, again, a parameter gamma times the difference between 2 points squared. This is very important. I will come back to this, but this does not include a dot product like we have in our polynomial kernel. Right? So here we have a dot product. Here we don't have that. Here we just have the difference between 2 points. And our parameter gamma here defines, it's also called the kernel width. It defines basically how wide or narrow our kernel is. So this is for gamma 1. This is our default kernel. See, it has a certain width. And you can interpret this as the influence that any point gets. Right? So if you have a point that lives in this space, it has a local influence around it, because you use a difference here. And the further away I get, the less influence the point has. Now, if I make gamma smaller, then my kernel becomes more wide. And our point here will have a larger influence. If we make our gamma very large, then this bell shape becomes very narrow, and our point will have only an influence just around its own location and nowhere else. So yeah, this is basically one of the most powerful kernels. And if you have to choose, like if you're stranded on an island and you can only bring one kernel function, I would bring this one. Okay. So as you can see, this expression does not involve a dot product. It's just it uses the difference between 2 points. So say that I have 2 points, x1, x2, and say I move x2 around. So here we have 1 point x at 0, another point around 2. In that case, the value of the RBF kernel, if I evaluate this function using a gamma, in this case 0.5, then this intersection here, this gives me the kernel value. So the kernel, the similarity of these 2 points is, in this case, 0.1. If our points get closer together, then obviously the similarity becomes bigger and the RBF kernel goes to 1. If they completely overlap, the kernel becomes 1 and the 2 points are completely similar. If it moves away again, you will see that the similarity drops again. Now, how fast this similarity drops, that depends on the width of the kernel. Right? So if we have 2 quite narrow kernels like here, the similarity will go down quite fast. If we make our, up to a point that, like in this case, the 2 points have very little influence on each other. Right? They're very non-similar. But if I make my gammas wider, so if I take a smaller gamma, my kernels become wider again, and the similarity goes up again. And so controlling gamma basically controls how much influence, how far the influence of a single point reaches. If I take a very small gamma, so a wide kernel, then every point influences every other one. If I take a very narrow gamma, every point will only influence a small region around it and maybe affect no other points. Okay, so yeah, so now we have seen 3 kernels, and we can basically choose whichever one we want when we want to use support vector machine. We can use a linear one, we can use a polynomial one, which gives a shape like this, or we can use a kernel, an RBF kernel. And you can see polynomial kernel gives you like these polynomial shapes. An RBF kernel will effectively, so in this graph, the points to the black circle are support vectors. And you can see around support vectors, you can see they have like an influence around them. And so all support vectors have this influence. Also the negative ones. And if you would count up the influence of all these points, you will get a shape like this one as well. Right? You will get a shape like this. Right? This is the boundary. This is the margin here. This is the other margin. Right? So this kernel is quite special because it has only every point, every support vector only has a local influence on the decision boundary. Right, to get to see this in a bit more detail, so say I have these points. Now remember our prediction of our support vector machine. So given the test point u, we predict the value, negative or positive, right? By taking, in this case, the kernel, not the dot product, but the kernel of our point x and another point u. So say you want to predict the value for point u here. Okay. Then we compute the kernel between u, right, and other points around. And again, like in this case, all these points have very little influence around them, so there's almost no influence on this point U, right? But you can control with the gamma in a minute. And so basically our prediction is the weighted sum of the kernel between our point and every possible support vector. So basically you measure the kernel between this point and all these support vectors times the learned coefficient of those support vectors, which are shown here. Right. So this point here is basically influenced by all support vectors, depending on how close they are and what their coefficient is. Now in this case, you can see that there's very little influence between this point and the other points. But if I would increase my gamma, if I would decrease my gamma, if I make my kernels wider, you will see that now all these points have more influence. And while initially this point was clearly on the positive side, change the gamma also changes things. It's still positive. It becomes more positive. But you can see that changing the kernel, the width of the kernel definitely has an influence on the points, on the predictions that we make. And you can see how the decision boundary is here very complex. If we make gamma small, so we make our kernels wide, then our model becomes increasingly simpler until we get this very simple model here. And even get some classifications. This is underfitting. This is correct. And this is obviously overfitting, right? Because basically we build boundaries around individual points, which is not so good. Right? So here is obviously overfitting. And we don't want that, right? Because if you want to make a prediction, so in this case, actually, this point is now predicted red, because only points directly around the blue points will be predicted blue. And this is an obvious case of overfitting. So we want to basically tune our gamma so that, well, given the complexity of our data, you find a simple enough decision boundary. Again, you typically cannot look at this data, but you would use the test score to tune this gamma. Make sure that it doesn't overfit or underfit. This second parameter, of course, is our C parameter. Remember, we had that's our regularization parameter. This C parameter adds a cost basically to any margin violations. So if we have a point of the wrong class in the margin or on the right side of the boundary, then this adds a certain cost to that. So we can make it a bit smaller. We can either make that cost very low, and that would yield very wide decision boundaries. And so here we have, you can see how large the margin is. Right? So it's around here. If we make C smaller, then our margin becomes wider. If we make C larger, then our margins become more narrow. Just putting more effort into making sure that there are no transit errors, so it will start overfitting. And again, this is something you will have to tune. Okay. So in general, we have two important parameters. There's gamma, the kernel width. If gamma is high, then we have narrow kernels, narrow Gaussians, which means more support vectors, right? Because if gamma is large, so if gamma is very large, yes, then we get every point basically becomes its own island, and every point becomes support vector. So it's obviously overfitting. Low values of gamma, so if gamma is too low, then our kernels are too wide, and basically everything overlaps, and we start underfitting. that's the case when gamma is very low here. You will get this one single ellipse basically around the blue points. Secondly, C, because of margin violations. So high C values punish any margin violation. So it will lead to narrow margins and more overfitting. If C is low, then you get wider margins, and because the margins are wider, more points fall into the margin, so you have more support vectors and also more underfitting. Here again, you have a matrix of this. So these are all RBF kernels, and we change the gamma value from left to right, and we change the C value from top to bottom. So for instance, in this top case here, we have very low C. So we have super wide margins. The margins don't even show, they fall off the image here. If we increase C, we can see that the margin shrinks, and here the margin becomes very narrow. If we increase gamma, however, then we start, so here's obviously underfitting. Here we start underfitting less, so this is better by the looks of it. And this is obviously overfitting. So here our gamma is too large, so we get very narrow Gaussians around our individual points. Typically, you want to start with something in between and then tune that to your data. And so if you look at the intermediate level, so here gamma is more or less correct. C here, yeah, it's still probably too small because every point is a support vector, which is not necessarily a bad thing, but it's not ideal because you have to remember every point in your data set. So if you have a large data set, it means your model becomes very large and very slow to make predictions with. If you would make C larger, you can see some points become no longer are no longer support vectors, so you have less support vectors. And well, here nothing changes anymore. At some point you will saturate, right? At some point you will have no more margin violations, and increasing C doesn't change anything anymore. And so you can see it here and here as well. Right? So tuning C and gamma is very important to get the optimal performance out of your support vector machine. This is an overview of what the different models look like on different types of data. So in this case, we have those two banana shapes. Our linear kernel tries to fit that with a line, but doesn't really, well, only gets 80% accuracy. RBF kernel can learn very nice blob shapes. So it actually learns these banana shapes. Well, it learns which support vectors are needed to make predictions, so that the predictions will be banana shape. And so you can see that the performance is much higher. The polynomial, yeah, it tries to fit a little of this data here, but it's in fact not much better than the linear kernel. At least not looking at the pure accuracy. In this case, you have two blobs inside each other, so it's like a donut shape. Again, a linear kernel has no chance of learning this. Our RBF kernel kind of learns this, right? It learns this blob and it learns this ring basically around it. So it's much better, 80% accuracy, while this is 40, and yeah, polynomial again doesn't work very well. And here we have just two blobs near each other. The linear kernel tries to fit that. Our RBF kernel can pick up more of the fine relationships here. And polynomial kernel tries to do the same thing, but it's slightly less good than the RBF kernel. Okay, so in practice, C and gamma always need to be tuned. I often see people just use SVMs without tuning, and I think generally that's a bad idea unless you're super lucky that the defaults, I mean, it has pretty good defaults, but still, I would always tune it to your data. Also, C and gamma interact with each other because they are both regularizers, right? We've seen this. So both gamma, so if you have a model that is underfitting, then increasing gamma will cause overfitting. If your model is overfitting, you can regularize. So let me start over. So if you have a model that overfits, you can regularize by decreasing gamma, right? This model overfits. You can fix that by reducing gamma. Vice versa, if you have a model that overfits, you can also reduce that by decreasing the C value. Right? So both are regularizers. And well, I would say that gamma is a stronger regularizer than C. But both are regularizers and both interact with each other. And because they interact, if you would actually plot the response surface for different values of C and gamma, you would often see that there is so lower gamma requires something like this. So this will be your optimal region. Typically, it's some ridge in this space. Although high gammas typically, like at some point, yeah. So this is underfitting, I think. This is overfitting. Although overfitting with a high gamma is very likely. Overfitting with a large C is less likely because at some point there's no more data in your margin, so you can't overfit anymore. It's very likely that if your gamma is large, you'll start overfitting. And this is the optimal range, basically, of values. So what you can do in practice is, if you have a good C, like you can start with a default or you can play around a bit. But if you have a good C, then you just need to fine-tune gamma and you're good. If you want to be absolutely sure, you can also do a grid search, or there are better techniques like Gaussian optimization, which we will discuss later on in the course. One important aspect of SVMs is that they expect all features to be on the same scale, right? Because you use dot products, and dot products for features on different scales kind of messes with your similarity. So you don't want that. So whenever you use an SVM, always scale your data beforehand. Okay? Normalize or scale so that your data is in the same range. Whether you use like standardization between 0 and standard deviation, or min-max between 0 and 1, doesn't matter so much, but always scale the data beforehand. Now, SVMs can be used to learn very complex decision boundaries, even if you have few features, right? So if you have a data set which has typically a lot of features, but a few points n, SVMs are basically unbeatable because they are, normally if you would have a high-dimensional data set, you need a large amount of points also to learn the weights. SVMs, because they use this kernelization, work pretty effectively in this case. So if you have data, for instance, patient data, which have a lot of information about patients, but you only have a few patients in your data set, SVMs are a very good method to use. So they work well on both high-dimensional and low-dimensional data sets, but they are especially good at these small high-dimensional data sets. You can't really inspect them, right? So normally, well, when you have your normal linear models, you can look at the weights per feature and you can see which features are important, right? In SVM, well, in the kernelized SVM, at least, you could, in principle, you can still learn the weights, right? The weight is basically a linear combination of your Q coefficients times the sign of your training point times the value of the point. So you could compute the weights for features if you wanted to. Another thing you can do is to look at the support vectors. Right? You can see which support vectors have a high A high coefficient, which means they have a big influence on the predictions. So looking at support vectors with a high coefficient tells you also something about what the model is using basically to make predictions. And in the labs, if you want to try this yourself, in scikit-learn there's the SVC, support vector classifier, and there's a range of kernels you can use, like linear, polynomial, RBF, sigmoid, and so on. There's also a support vector regressor for regression, and we'll see in a minute how that works. Now, there are many other possible kernels, and when a kernel does not exist, we can still pre-compute the kernel matrix. Right? So remember, the kernel matrix is basically the matrix of all the possible all the possible kernel values. Let's say k is kernel of x1, x1, kernel x1, x2, and so on. So it's the whole matrix of these possible values. So if you can pre-compute that for all your points n, then you don't need the kernel function. You just need the kernel matrix. Right? Which means that if you have some similarity measure, which is defined in some way, which already exists, you can compute similarity between all your points, come up with a kernel matrix, and use kernelized SVMs. Right? A typical example for this are text kernels. So these are kernels for text. So there are different kinds. So one of them is word kernels, where you first construct like a bag of words, like you have all the words in your text. So and then you compute basically the number of times that word occurs in every text, and you can then use TF-IDF to scale that. And then if you have 2 points, x1, x2, so high-dimensional vectors, your kernel could be just the inner product between those vectors, and then you can build your kernel matrix, and you can use kernelized SVMs. Another thing you can do is look at subsequences. So if you have a text, you can look at whether there are subsequences in both texts, and if that occurs, then those two vectors, those two strings are similar. Right? You can do the same thing for any other sequence. So if you have that, you can do like the length or the number of common subsequences. You can compute a similarity with that, and you can then again build a kernel matrix. So text kernels were all the rage a couple of years ago, but these days they are replaced with deep learning embeddings, which can be trained on a lot more data and are therefore typically better in most applications. There also exist other things like text kernels, there are graph kernels, or image kernels. Same idea. Whenever you have some similarity function, you can use that to build a kernel matrix, and you can use kernelized SVMs. The final question we want to answer is, okay, so we can kernelize SVMs, but can we also kernelize all the loss functions? Because the loss functions we've seen so far never had a dot product, in them except for the dual SVM. Now, there's a nice theorem called the representative theorem, which states that, which basically tells you whether you can kernelize your loss function and how. So it says that if you have a loss function of this shape, which is the sum of any arbitrary loss function using any function of our inputs x, plus a regularizing term, which has to be non-decreasing. This could be like L1 or L2 or something else, and a constant lambda here. This is our regularization coefficient, right? If your loss function has this shape, then it says that the optimal weights can be described as a linear combination of your training samples. So again, dual coefficient times the training label times some function of your inputs x. Right? So first of all, appreciate that this is exactly what we found for SVM. The only difference with an SVM is that we don't have to do this over all endpoints, but we only have to use this for, you only have to do this for a smaller set of support vectors. Like typically the number of support vectors is much smaller than the number of data points m, which makes this much more efficient. But in general, you can this whole thing. So effectively, what the representative theorem tells you is that we could have come up with the dual formulation of the SVM without going through all our Lagrange multipliers. It just follows directly from the representative theorem as well. The interesting thing is that this loss function here is pretty general, and this also applies to ridge regression. Remember, so L ridge was something like the sum over y minus wx, right? Squared, the sum of squares, the sum of squared errors plus the sum of all the weights squared for L2. Right? This fits this description, right? So this matches this shape. So this means that we can kernelize ridge simply by replacing this W with this linear combination of the infinite side. It's also true for logistic regression, right? Logistic regression was basically log loss plus L1 and L2. Perceptrons had the perceptron loss, right? And support vectors have hinge loss, right? So they all agree with this formulation and they can all be kernelized. So to give you just one example, let's look at kernelized ridge. This looks like a very scary slide, but it's not so bad. So remember, this is what our ridge loss was. So it's basically the sum of squared errors plus the regularization term. Now, if you want to come up with the dual formulation of this, or the kernelized, well, let's first do the dual. Right? So to get the dual, all we need to do is to replace this W by this. Right? So if you put this in on all these points, you get this. This is nothing else than this. This is the same loss function. We just replace W by the sum, and then we get this. Now we see that we only have dot products here. Right? So instead of computing the loss in terms of the weights of the features, we compute the loss in terms of the dual coefficients of our data points. And we just have to learn these dual coefficients of the data points. And because now the inputs only occur as dot products, we can just replace these dot products by any kernel of our choice, and we're done. And now we have kernelized ridge. Now, to understand this better, let's see what happens as this algorithm is learning these dual coefficients. Right. So here we have 6 points, the blue points here, and we want to fit a function through these points. Now, because we use an RBF kernel, each point will have a local influence around it, right? So this red line, which is nothing more than a linear combination of the learned kernels, of the kernels times the learned coefficients. Basically, it means that every point has a local influence on this red line here. Now, I've already filled in the coefficients for the last tree, but we can play with the first tree. So you can see that as we change these values, if this becomes negative, then it's negative times this kernel. So we can see it goes down. It locally influences this line here. Right? So basically what the algorithm needs to do is learn the coefficients so that it fits the training data. So probably something like this would be a good solution. So it goes more or less to the points. Again, our gamma parameter controls the complexity by controlling the width of these kernels, or more precisely by controlling the influence that each individual point has. If we make these gamma values smaller, our kernel becomes wider, and you can see that our curve becomes flatter. And in the extreme, it becomes a linear function again. Right? If we make gamma larger, you can see it becomes, this is nice fit. If you make it too large, then it will fit every point exactly, and it will more likely overfit. So I hope this makes it clear. We can also just plug in the kernel-rich algorithm inside the run and see what happens. So here again, we have our regression data, and we use kernel-rich. And we see again, we can learn a nonlinear function using rich regression basically by just adding a kernel, right? So that works perfectly. And we can also again change the gamma parameter. If we make gamma smaller, our curve will become flatter. It becomes a straight line in the extreme, and if you make it too large, it will start overfitting individual data points. Now there are other kernelized methods, of course. We can use the same procedure as we used here. Basically take the loss function, plug in this expression for W, and then we end up in the end with our, first of all, the dual formulation, which we then easily kernelize. So in the same way, you can do this for logistic regression, and you get an equally scary loss function at the end. For perceptrons, things are a bit easier because they do incremental updates. We saw there that the loss of an individual point was defined by whether that point makes a misclassification. Right? If it makes a misclassification, it means that either yj is negative and yi is positive, or vice versa. So if it makes a misclassification, then we use to update the weights of our perceptron by replacing the weights with the sum, linear combination of our coefficients with the kernels. We gain this function, and this, if you do this, then basically what happens is that instead of updating the weights, you update the dual coefficients. So every time you have a data point which you misclassify, you add 1 to the dual coefficient of that data point, which means the data point is more important to get right. Okay, and we can do the same thing for support vector regression, of course, but you will actually see that this is quite similar to kernel-rich. In fact, the model that is a support vector regressor and kernel-rich want to compute is exactly the same. They learn exactly the same model. They just use a slightly different loss function, which means the results will also be slightly different. Okay, that's it. So in this lecture, first of all, we saw that if we have a linear model and it does not fit our data well, we can use feature maps to map our data into a high-dimensional space, and in that high-dimensional space, we can learn a linear model that hopefully perfectly fits our data, or better fits our data. The problem is that computing these high-dimensional spaces is very expensive and slow. But for some of these feature maps, we can compute the dot product in this high-dimensional space without actually constructing this space. Right? This is called the kernel trick. The kernel is basically a function two inputs which computes the dot product of these 2 points in a high-dimensional space. And for some of these, we have an analytic solution for that, so you don't have to construct those spaces. The kernel is therefore also called the generalized dot product. It's nothing more than a dot product in a high-dimensional space. And you can see this as measuring a similarity between 2 points. There are many such kernels. We've seen the polynomial kernel, which analytically looks like this. So if we want to fit a linear model in a high-dimensional space, we can do that by computing dot products, and the dot product ends up being just the dot product in our original space to the dth degree. It has these 2 extra parameters which allow you to play with this, but these are optional. The RBF kernel looks like this. This actually constructs a positive infinitely high-dimensional space, or it computes the dot product in this infinite high-dimensional space, and it evaluates like this. And the RBF kernel, very importantly, looks at the difference between 2 points. So it's a local kernel, and it results into every point having only a local influence in your final decisions. And if you have a problem for which a kernel does not exist, for instance, text or graphs, you can use any existing similarity score to build the Kernel Matrix, which is a matrix of all possible kernels, combinations of xi and xj. That's fine. If you have a kernel matrix, then you can equally easily use any kernelized method like a support vector machine in this space. So theoretically, any loss function where the inputs appear only as subproducts can be kernelized. This is true for linear SVMs. And the representative theorem tells us which other loss functions can also be kernelized. And this turns out to be possible also for ridge regression, which gives us kernel ridge, logistic regression, and perceptrons, and actually some other methods as well. That's it. I hope you enjoyed this lecture, and I hope to see you next time.